Alright guys, today what we're going to be discussing is static electricity. And so we're starting kind of the last little leg, guys. Starting the last little leg of topics that kind of leads us to the end, which is electricity. So it's kind of the last big topic. You know, we have motion beginning, and then we move into like waves and energy, and then now we're electricity. So it's kind of like the last unit.
You just realized? There's only one person in the whole class that seen your last day.
You had the first part, right?
Okay, so we talk about static electricity a lot. You know, if you're walking with socks on across the carpet, we'll talk about building up static electricity. Or if you get out of the car and then touch some metal, it zaps you.
Every single time I get out of the car and it's irritating.
Well, actually, it depends on how you get out of the car. If you kind of slide out of the car, then that tends to build up more static electricity. If you just, no, not hop, but I mean, if this is you sitting in the car and you do this, then that builds up a lot of static electricity. But if you just get out of the car,
you drift into your parking spot and just open the door and you just fling out. It's gonna build up more.
If you just take your front windshield off and just slam on the brakes and then just go out the front. That might not be the best. Don't do that. Of course, then I would assume that your car would still be moving, and so then you're on the pavement and your car's coming.
She pulls up the e-brake.
Yeah.
That would stop the car.
So that guy right there, you want to take his advice. All right. So the study of static electricity, static charges, is called electrostatics. Anytime we're talking about static electricity, what we mean is I have a collection of charge, either positive or negative, that it's not in motion. Okay, so we're not talking about like the kind of charge or the kind of electricity that comes from the wall. Okay, from the wall we have a movement of charge. We're talking about I've just built up some charge and it's sitting there. Okay, that's static electricity. Okay, anytime I have charge being built up, whether positive or negative charge, we always know that charge is being collected by either gathering or releasing electrons. It's always electrons. Okay.
Is that a silly?
That's one good spot there.
Yeah.
That's a good spot.
Party in the back.
Can Timothy static ball?
Let's
see if Timothy's new hair.
Well, we'll try it in a little bit and see what happens.
Dang, man, that's a new style.
This is a little hair. Don't touch the hair.
Okay, so anytime we're talking about charge, there's two words that we typically use in charge. The two words would be positive and negative. Okay, and when we're talking about negative charge, we're talking about gathering electrons. Okay, because an electron has a negative charge. And since the only thing that moves is an electron, then to gather positive charge, we would lose electrons. Okay? So if I'm gathering electrons, we say that I'm collecting negative charge, or if I'm releasing electrons, we say I'm collecting positive charge. Okay, so that's kind of, it seems backwards to say collecting positive charge when I'm losing electrons. That's really the way it is. Guys, to me, if I say collecting positive charge, that would mean adding protons, right? Because protons are positively charged. Okay, however, if I add or remove protons, what's happening? It's changing elements, right? So I mean, if I have hydrogen and I add a proton, now I have helium. Okay, so we're not moving protons; we're just moving electrons. But I could charge something by adding a proton. I could add a proton, and then I would have a positively charged helium atom if you did it correctly. I don't know the mechanics of adding a proton. I don't think you just take some tweezers and add a proton in. I think it's a little bit more complicated than that. By the way, guys, where did the words positive and negative come from?
That's a good question.
Why do we call an electron negative? Why do we call a proton positive?
That's what the guy said. It was supposed to be.
Huh?
Who is it that go around?
What now?
The person that cut the out.
To be honest, I have no idea. There's really no good reason. I mean, there's nothing innately negative about an electron. I mean, it doesn't have a bad outlook on life, and you don't lose things when you get electrons. That wouldn't typically when we say negative. If I get negative dollars, I'm losing dollars. So it's not negative in that sense, and it's not negative in the kind of the type of molecule you wouldn't want to be around. We really could call it an electron has red and a proton has blue. I mean, the names really don't matter. It's just that's the characteristic that it has. Okay, so if I say something is negatively charged, the whole point of that is to tell me that it has a buildup of electrons. Okay, so it's not. I could say it has a blue charge. Oh, well, that's a buildup of electrons. Okay. So that word doesn't really matter all that much. Okay. Eh?
Yeah.
Good? So far, so good? Okay. So, anytime charges are separated. Okay, so be it an electron or a proton. And there's a problem with this picture. What's the problem with that picture? If I'm using positive, let's say
we're coming together.
well,
Generally negative
what-
is red.
if I'm if I'm letting this represent one proton and one electron, what would be the problem? I mean, a proton's just way bigger. Yeah. So that would be the problem. But we'll let that be a positively charged object and a negatively charged object. That way they can be the same size. Okay. So when I separate charge, guys, an enormous amount of force, either attractive or repulsive force, is created between those. When I say a huge amount of force, I mean many times the gravitational force. Okay, gravitational force is very small with respect to the electric force, and we'll calculate tomorrow the difference between those forces. And we'll find the electrical force to be many thousands of times greater.
Does negative attract positive?
Yes. Okay. So opposites attract, and the same charges repel. Okay. So up here I have a positive and negative. I know that they would come together. Okay. And if I changed one of those to a negative, then we would know that they would separate and they would repel. Okay. Okay, so a little example of that. This is called a Van de Graaff generator. And a Van de Graaff generator builds up electric charge. And specifically it builds up static charge. And I'll show you all just a little bit how it does that. But on this little, the top up here, it tends to build up negative charge. And here this is just connected to ground. And so since what we'll see is this ends up building up a little bit of positive charge. And so since there is an attractive force between positive and negative, then what we see is those charges are capable. Huh? It's okay. I don't know why it does that. But that charge can be force between those. Okay, essentially what's happening, guys, the electrons that are building up here are just getting like a huge amount of force that's surging them through the air. Oh, that was a good one. Okay. The same thing can happen to me, guys, since I'm connected to the ground. I mean, it can get me pretty good. Yeah, it hurts. Yeah, no, that's not fun.
He said, Jay, it's so funny.
I tell you, if you're a Star Wars fan, you just can't resist it.
That is the best show to watch. I love that.
Take that, Luke.
The movies are hilarious. Ron Dunn died.
So, on a microscopic level, guys, charging is really taking place on the atomic level. So, I mean, it's not really something we can see. Side note: have we ever seen an electron?
No.
Yeah. No, we have not.
I've never seen one.
But I mean, have we ever seen like, oh, taking a picture, there's an electron?
No.
No. Okay. So how do we know an electron exists?
It just does. It just does.
I mean, it's not like
charge.
it's not like I do believe in spooks.
It's
I do
metaphysical.
believe in spooks kind of thing. I mean, like, yeah. I mean, we can't just like get a little
Because
cube
it
of
can be measured.
electrons, huh?
Because it can be measured. Can it be measured?
Okay. So essentially, guys, we've seen. You do tests, and the tests lead us to believe that an electron exists. I mean, that's the only evidence that we have that there is an electron. Is we've gone through these tests, and the tests suggest that there needs to be a particle, and we'll call that particle the electron. Okay. Yeah, that's really the same thing with quarks. Okay. Never seen a quark, but never heard of a quark. The quark is the particle that makes up the proton and the neutron. Six different quarks. Those are the up and down and strange and charm and top and bottom, of course. Y'all haven't heard about quarks?
No.
We'll get there.
AC chemistry.
We'll get there. So, as y'all know, guys, the nucleus of an atom is positively charged. Okay, and we call the electron cloud negatively charged. Why did we switch over from the Bohr model to the electron cloud?
This is more accurate.
It's more better. That's exactly it. Huh? I mean, if we let's investigate a hydrogen atom. A hydrogen atom, one proton, no neutrons, and a typical hydrogen atom. And so if we let a hydrogen atom, if we let the proton be 1 foot, if we're making a model, if I let the proton be 1 foot across, then the width of the hydrogen atom would need to be 100,000 feet, okay, in diameter. So if the proton is 1 foot, the whole atom would be 100,000 feet, and the electron, which would be what the size of a flea, would be somewhere in there. Okay. So we don't really know where it is, so we'll call it an electron cloud instead of saying, oh, well, it's here. Who knows where it is? Okay. That makes sense?
Yep.
Okay, so therefore, if the electron cloud is negatively charged and I charge an atom, that means I'm adding electrons to the electron cloud, or I'm removing electrons from the electron cloud. Okay, so when charging is occurring, electrons are either being added or removed from individual atoms. Okay, that's with the exception of metals. Metals are a little bit different. But metals, they have what we kind of call an electron soup almost. In the outermost shell of a metal, the electrons aren't typically held to the metal. They just kind of flow around wherever they want to go.
Electrons.
Yeah.
What's it like? Electronic band.
Well, no.
Electron soup. And they would make like techno music and
I don't know what you're talking about.
Let's fix this.
Why would somebody want to make electrons?
All right, guys. Conductors and insulators. Remember, with heat, if heat could flow through something through conduction, we called it a conductor. And if heat didn't flow through something very well, we called it an insulator. We'll have the exact same thing with electricity. And so, in electricity, a conductor is a material through which charges can easily move. Okay, specifically electrons. Okay, so in a conductive material, electrons can easily jump from atom to atom. Okay, so infer what an insulator will be.
I thought you said charge
Cannot easily move, okay? So in an insulator, guys, a material through which charges cannot easily move. Give me some examples of insulators. What do we use to rubber, air, plastic, glass? Okay, those are all materials through which electrons do not easily move. What about water?
No.
Okay, water, pure water, like distilled pure water, is actually a insulator. Okay, and even tap water is a pretty good insulator. However, if you add something else to it, add some salt, add something else, then it can conduct electricity better. And on the atomic level, what makes something a conductor or an insulator is going to depend on the attraction of those outermost electrons to the nucleus. Okay, the stronger the attraction between the electrons and the nucleus, the harder it is for the electrons to move, and the harder it is for the electrons to move, the better of an insulator it is. Okay, so when we're talking about a metal, we said that outermost band really isn't attached to the atom; it just kind of flows around at will. Okay, and so those are good conductors because those electrons just flow very easily. This is going to explain why. Later we're going to talk about the amount of energy lost going through an insulator or going through an insulator. Yeah. And you lose some energy when electricity flows through an insulator because it takes a certain amount of energy to pull those electrons away from the atoms. Okay, and that ends up turning into heat. But however, guys, just because something is an insulator does not mean it does not conduct electricity. I mean, you don't want, if lightning strikes a pool, you don't want to be in the pool, but water's not a very good conductor. Okay. Okay, so air is a fantastic insulator, but lightning, every day lightning strikes and carries a huge amount of electrons from the cloud to the ground. I'm sorry, I didn't draw it. Call Microsoft. How dare you put a bundled up sock as a cloud in your word art? No, not word art, clip art. And so in order for an insulator, guys, to carry charge, there must be a great amount of force on the electrons. Okay, later we're going to call that force voltage. Okay, yeah, we'll get there. But and actually, when air conducts electricity, it actually doesn't really become air anymore. It becomes something else. It's called ionized air, which is actually a plasma. So that's what's happening up here. It's momentarily turning into a plasma, which is at very high temperature. All right. Any questions on charge?
Wait a second, I need a comment.
I'm just going to stop the recording. Is there any questions?